Okay, so let's get started with the last session. So it is my pleasure to introduce Steve Dong, my colleague at Puddle University, to give the last lecture. So Steve got his PhD in State University of New York at Buffalo. And then he did several years of a postdoc at Brown University with George Kanitakis before joining the faculty of Purdue University at 2006. And he's now a full professor of mathematics at our department. So Steve is an expert on spectral element method and computational fluid dynamics. So in the past, he has done great work on direct numerical simulation of turbulence, including particularly the bluff body turbulence and the Taylor-Couette turbulence simulations. And in recent years, his effort has been concentrated on developing models and the numerical method for multi-phase incompressible flows. And that's what he's going to talk about to us today. So let's welcome.
Thanks, Jay, for the kind introduction. Thanks to everyone for staying and being here. This is the very last talk of this conference, so thank you very much for coming. In this talk, I want to share with you a problem we have been looking at for the past few years. The multiphase flows consisting of n immiscible incompressible fluids. So here n is an integer of 2 or larger. One example of these problems is the air-water-oil system. So with a slight abuse of notation, I will call these problems n-phase flows. So here n refers to the number of different fluid components in the system, not necessarily the number of material phases. For example, with the air-water-oil, I will call them 3 phases, but actually there are only liquids and gas in the system. So we'll consider how to model and simulate these problems with high-order methods. This figure shows the equilibrium configuration of a compound water-oil drop on a solid wall with different contact angles. And this is computed using the methods that I will talk about in this, discuss in this talk. So let me first define the problem. We are going to look at an isothermal mixture of n immiscible incompressible fluids. So because the fluids are immiscible, so any pair of the fluids can form an interface which will be associated with the surface tension. And any 3 fluids can form a 3-phase line. So the problem will involve multiple types of fluid interfaces, multiple pairwise surface tensions, and multiple 3-phase lines. There may be other complications. For example, the problem may involve solid walls with certain wettability properties. So there may be multiple contact lines and multiple contact angles. And there may be open boundaries in the system. Multiple types of fluid interfaces may pass through the open boundaries. So we'll consider how to model and simulate these systems with high-order methods. I specifically have the high-order spectral elements in my mind. These problems have numerous applications in reality. This slide only shows a few examples in functional surfaces, in the optofluidic devices and liquid metal batteries and oil spill, of course. So one type of functional surface is the so-called liquid-infused surface, which typically involves the fluid such as oil and water drops on a solid substrate. The whole system, of course, is in the air. And this is a so-called liquid core, liquid cladding optofluidic waveguide. There are other applications. This is the paper from MIT in Nature a few years ago. They used 3 molten metals for making the liquid metal batteries. And there are other applications, so I will not go into details. So why do we care about n fluids, especially for n equals 4 or more? We know for 3 air, water, oil, but for 4 or more, why do we care about them? Does there actually exist 4-phase systems or more phase systems? The answer is indeed positive. There are several materials in the liquid state near the room temperature. Besides water, oil, mercury, some metals such as the gallium and gallium-based alloys are such examples. So these liquid metals have usually superior thermal and electrical conductivities, which can be used for efficient cooling of electronics and for making batteries, for example. In this talk, we are going to consider 3 questions: how to formulate such systems mathematically, how to solve them numerically, and what's the physical accuracy of the method. So these questions will basically serve as the outline of this talk. Before we delve into the details, let me first briefly mention some related work. A number of researchers have contributed to these areas, especially Kim, Boyer, and others. So this slide only shows a incomplete list of these contributions. Now, given a system of n immiscible incompressible fluids, how do we model and formulate the system? 2 physical properties turn out to be important: thermodynamic consistency and a reduction consistency. Thermodynamic consistency refers to the property that the mathematical formulation must satisfy the conservation laws and thermodynamic principles. The reduction consistency is based on the following observation. Given a system of n fluids, if some of the fluid components are absent, such that only m fluid components are present in the system, for example, if you have only, if we consider air, water, oil, but oil is absent, then this n-phase system is physically equivalent to the smaller n-phase system. That's if only m fluid components are present in the system, then the n-phase system is physically equivalent to the smaller m-phase system. So with that air, water, oil, if oil is absent, so this 3-phase system is physically equivalent to the 2-phase system consisting of air and water only. So that's correspondingly, we will require that the mathematical formulation for the system must satisfy the same property. That is, if only a set of m fluids are present in the n-phase system, then we require that the n-phase formulation must satisfy, should exactly reduce to the corresponding n-phase formulation. So that's we call this property the reduction consistency. So why is reduction consistency so important? That's because the n-phase system, if you think about it, n-phase system is locally equivalent to a smaller m-phase system. That is, at any point in space, not all, because these fluids are immiscible. So at any point, at any point in space, not all fluids are present. So only m fluids may be present in any region. For example, in the bulk of the fluid, only 1 fluid is present. Near the fluid interface, maybe 2 fluids are present. Near the 3-phase lines, there maybe 3 fluid components are present. So the point here is that only m fluid components may be present at any point in space. So correspondingly, the mathematical formulation for the system should satisfy the same property. So that's the reduction consistency. We'll show that the reduction consistency is critical to capturing the physics of n-phase systems accurately. Now, the thermodynamic consistency is a little easier to deal with, but the reduction consistency turns out to be much harder to satisfy. So we'll concentrate on the reduction consistency. But first, let's look at the thermodynamic consistency. So with the thermodynamic principle, these conservation laws, second law thermodynamics, etc., and several assumptions, and we can rigorously derive a thermodynamically consistent n-phase model. There are several ways to do this. So, but let me only show you one model, one thermodynamically consistent model based on the phase field approach. You don't need to bother with the details. Let me only point out that the dynamic variables in this system is the velocity, yield, pressure, and n-1 independent volume fractions in the system. Ci is the volume fraction of fluid I within the mixture. There are 2 other important variables. W is the free energy density function of the system, and Mij is the mobility matrix, which must be a symmetric positive semi-definite the matrix. Now, given any the free energy density function and the Mij, the mobility matrix, this system is thermodynamically consistent in the sense that it rigorously satisfies the conservations of mass, momentum, the second law of thermodynamics, and it is Galilean invariant. So let's ask the question, is this model reduction consistent? If only m fluids components are present in the system, does this model reduce to the corresponding the model for the n-phase system? The answer is no in general. So how do we satisfy the reduction consistency with this model? So that's the central question we want to answer. Now, I want to specifically consider 3 reduction consistency conditions. That is, if only a set of m fluids are present in the system, in the n-phase system, we will require that the free energy density function, the governing equations in the boundary condition for the n-phase system should exactly reduce to those for the corresponding n-phase system. So these are the conditions we'll consider. But actually, we're only going to consider the governing equation. Don't have time for the boundary condition, etc. But I will show some results with the boundary conditions. All right. In order to come up with a method for systematically constructing reduction consistent formulations, we need to introduce several concepts. First, let's define the reduction transform. This is a little misleading. I mean, it's not exact the definition, but it's the definition in the paper. So basically, given a system of n fluids, we remove the kth fluid from the system such that the fluid K is absent from the system. The volume fraction of fluid K is identically 0. We call this operation reduction operation. And then we need to consider how the variables, functions, equations transform under the reduction transform. Based on the transformation properties, we will introduce two important set of variables called a reduction consistent set of variables and a reduction compatible set of variables. So under the reduction transform, if fluid K is absent, then the n-phase system will reduce to the corresponding n-1 phase system. Now, it's important to recognize the corresponding relations between the original n-phase system and the resultant n-1 phase system. So given a system of n fluids, if fluid K is absent, then the fluid 1 and to fluid K-1 will exactly correspond to the fluid 1, fluid K-1 in the resultant system. And fluid K+1 to fluid N will correspond to the fluid K and K-1 in the resultant system. So that's this correspondence relation. Now, based on this correspondence relation, we can define a reduction consistent set of variables. If we're given a set of n variables, say Vi may be a function of other variables such as the volume fraction, etc. We call this set a reduction consistent set if it transforms as below under the reduction transform. That is, if fluid K is absent, then the kth variable will become 0 identically, and the other variables will exactly follow the correspondence relations given on the previous slide. That is, the variable 1 to variable K-1 will reduce to the corresponding variable 1 to K-1 in the resultant system, and the variables K+1 to variable N will reduce to the variables K to the variable N-1 in the resultant system. If that's the case, we call this a reduction consistent set of variables. One example of this is the n volume fractions of the n-phase system. Correspondingly, we need to introduce another set called a reduction compatible set of variables. This set is related to the reduction consistent set, and actually the condition is a little weaker. So basically, under the reduction transform, if fluid K is absent, and if there's no restriction to the kth variable in this set of n variables, but the other variables will reduce exactly to the corresponding, follow exactly the correspondence relation given on a previous slide. That is, these variables there. But notice that the difference is that there's no restriction to the kth variable. If that's the case, we call this reduction compatible set. Of course, a given reduction consistent set is also a reduction compatible set. Now, one example of this is the densities of the n pure fluids. Notice that that's the pure fluids, not in the mixture. So similarly, we can define a reduction consistent set of variables, Vij. This is sort of like a tensor in theta space. And reduction compatible set of variables, Vij, and reduction consistent variable, single variable, V. So reduction consistent compatible set Vij, that's the pairwise surface tension sigma ij, is actually an example of the reduction compatible set of variables, Vij. All right. So with this definition, we can deduce many useful properties of the reduction consistent set and a reduction compatible set. For example, if Vi is a reduction compatible set, Wi is a reduction consistent set, then the contraction of them is a reduction consistent variable. And if Vij is a reduction compatible set, Wi is a reduction consistent set, then the contraction of them is a reduction compatible set of variables. There are many of these properties that will be important for basically proving that we can get a reduction consistent the equations. All right, so with this definition, we can introduce the reduction consistent set of equations. If we're given a set of n equations, Vi equals 0, so Vi may be a function of C or other variables, we call this a reduction consistent set of variables if the set of Vi is a reduction consistent set of variables. So you can see that if this is a reduction set of equations, n equations, if that's reduction consistent set, then when fluid K is absent, the kth equation will become identity based on the definition. And the other equations will reduce exactly to the corresponding equations in the smaller n-1 phase system. And we can similarly define a reduction consistent equation V equals 0. That is, if the V is a reduction consistent variable. I didn't define that, but basically that's, so it'll be the same if they reduce exactly to the variable corresponding to the smaller system. So with this, basically you can see that when fluid K is absent, this equation will exactly reduce to the corresponding equation in the resultant system for the reduction consistent equation. So with this preparation, we can state the method for constructing the reduction consistent, basically to show that the n-phase, the model is reduction consistent. So with the thermodynamic consistent model given on the previous slide, we have this result. So if the mobility matrix is a reduction consistent set of variables, and a dWdCi, W, notice that is the free energy density function. That's the derivative of this is a reduction compatible set of variables. And dWd, the gradient Ci, this is a reduction compatible set of variables. Then we can show that based on those properties, the set of n-phase governing equations given on the previous slide is fully reduction consistent. So that's the result. So the method would be that if we can find a reduction consistent set of variables for Mij, find the free energy density function such that these two each forms a reduction compatible set of variables, then this will give us a fully reduction consistent model, n-phase model. The question is, do such functions actually exist? The answer is positive. One example is given here. If we define the free energy density function in this way, define the Mij mobility matrix in this way, then we can show that the conditions for the previous theorem are satisfied. And then this will give us a fully reduction consistent n-phase formulation. Now, I want to point out that this is only one example, one way to satisfy the conditions for the theorem. There are many other ways to satisfy these. So there are many possible forms of fully reduction consistent n-phase formulations. So if we use the Mij defined on the previous slide and the W on the previous slide, and then this will give us this fully reduction consistent and thermodynamic consistent formulation. Now, if we can show that, based on the theorem, if only m fluids are present, then this set will exactly reduce to the corresponding n-phase system. Now, there's one complication. That is, in this model, the Mij and the mobility matrix, these are field functions. They are not constants. So if that's a constant, is basically, I think, is impossible. Pretty sure, but I cannot show that. But it's not possible to make a fully reduction consistent the n-phase formulation. So let's next consider how do we solve this system numerically. Now we can devise discretely energy stable schemes or semi-Blissic splitting type schemes. Because our model is fully thermodynamically consistent, it is possible. This makes it possible to devise energy stable schemes. Each type of these schemes has its pros and cons, but at this stage, we'll only consider the semi-Blissic schemes because of the simplicity for implementation and also the low cost per time step. So we have a very simple goal in our mind. So we want to develop a scheme such that to achieve this goal, that is, if you have a single-phase Navier-Stokes solver, I want you to use this algorithm and your solver to compute multi-phase problems with maybe very slight modification. So specifically, I want to develop a scheme such that on a discrete level, the scheme we only need to solve Helmholtz-type equations with constant coefficients, something like that. If that's the case, then the implementation using C0 high-order spectral elements will be very straightforward. So there will be no difficulty. So basically, our goal is that we want to develop a scheme. After discretization, the scheme will lead to a sequence of decoupled individual Helmholtz equations with constant coefficients. Now, there are several issues we need to overcome in order to achieve this goal. So most of these issues are related to the variable properties, such as the variable mobility matrix, variable density, variable viscosity, and couplings. Now, most of these issues are not new. They are, for example, the couplings. This has been well studied in single-phase flows. The variable density, variable viscosity also encountered in two-phase flows. And what is probably new, that's the variable mobility matrix. And only this one that's also partially new, because two-phase will also have the degenerate mobility, etc. But with the variable mobility, the problem is that if you use the conventional methods, and then you're going to end up with a variable coefficient matrix for example, for the pressure linear system after discretization. This means that you need to recompute the coefficient matrix frequently, or probably every time step. This computationally is too expensive. And with a variable viscosity, you're going to end up with a variable coefficient matrix for the velocity, and then you need to recompute the coefficient matrix every time step. So here, the variable mobility matrix is not quite clear, how to do that, to discretize that. So fortunately, in the past few years, we have developed, several ideas. Actually, a very simple idea to sort of, deal with this, at least for the semi-implicit schemes. So we are going to use a very simple idea to deal with these variable properties. So for example, with the variable density, we're going to do a reformulation of the pressure term. So here, rho is a field function. So we are going to introduce a constant term, rho 0. That's a chosen constant, must satisfy certain conditions. And then add this term minus this term, and then treat this term implicitly, treat this term explicitly. It's very simple. We cannot prove that these will be stable, but in reality, if you do that, it is indeed stable. But rho 0 must satisfy certain condition, must be smaller than the minimum of these the field, the rho here. Now, similarly for the variable viscosity, we introduce a constant term, add that, subtract that, treat this term implicitly, treat this term explicitly, and then eventually this will lead to the constant time-independent coefficient matrices for the pressure and the velocity. So everything will be fine. You can basically recompute the coefficient matrix and do just like what you encounter with the single-phase incompressible Navier-Stokes equations. Now, with the variable mobility matrix, we are going to do a reformulation of the variable mobility term. Basically, we are going to add these two terms, two sort of zero terms. Here, Ci star is an explicit approximation of Ci, and kappa 0s, these are chosen constants that must satisfy certain conditions. Basically, these are the zero terms. And we treat this term implicitly, treat this term explicitly, and the variable mobility term explicitly. And then with these, and then eventually, the n-1 coupled phase field equation with variable mobility matrix can be reformulated into 2 times n-1 decoupled individual Helmholtz type equation with the constant coefficients. So basically, after these, you can just like, as what do you do with the single-phase Navier-Stokes equations. So here's basically that's the algorithm. From those models, that fully reduced consistent, thermodynamic consistent n-phase model, we do a reformulation of the pressure term, do a reformulation of the viscous term, and reformulate the variable mobility term using the ideas on the previous slides. And after that, we employ a splitting strategy from the single-phase Navier-Stokes equations. So any of your favorite splitting scheme, and then this will give us a semi-implicit scheme. So with this algorithm, we only need to solve a sequence of decoupled individual Helmholtz type equations. There are actually 2n plus 2 equations. That's the phase field equation plus several of the velocity and the pressure equations. And all these equations involve only constant time-independent coefficient matrices. So you can recompute the coefficient matrices and use them later, save them for later use. And these can be implemented using C0 spectral elements in a straightforward way, very easily. Basically, if you have a solver for the Helmholtz equation, and then you can use this algorithm and use your solver to simulate multi-phase problems. So that's basically, that's the goal we have achieved. All right? So let me next show you some simulation results to demonstrate two things. One is the physical accuracy of the method. The other is the importance of the reduction consistency. So the first problem is a three-phase problem, the so-called floating liquid lens problem. Fortunately, these are all 2D simulations that don't have the 3D simulations. So here, rectangular domain, top, bottom are solid walls in the horizontal direction periodic. And initially, top half of the domain is air, bottom half is water. We have a oil drop, initially circular, that is held at rest on the water surface. At t equals 0, the system is released and starts to evolve, eventually reaching an equilibrium configuration. Our goal is to study the equilibrium configuration of the system. Now, the equilibrium configuration is a balance determined by the balance of several forces, the gravity and the three pairwise surface tensions. So from physics, we know that when the surface tensions are dominant, the oil drop will form a liquid lens that basically it will consist of two circular caps in 2D or two spherical caps in 3D. And if the gravity is dominant, the oil drop will form a puddle, a liquid puddle. So this figure shows the equilibrium configuration corresponding to a zero gravity. Indeed, these dashed lines, these are circles. Indeed, this shows that the profile of the oil drop consists of two circular caps. And this corresponds to the normal gravity. In this case, the gravity becomes dominant, and the oil indeed forms a puddle. Now, you may see that there's the star-shaped, there's a triangle there. So because that's when visualize these, I show the contours of the Ci equals 1/2. In this region, there's no fluid that has a volume fraction larger than 1/2. That's because of the visualization. So that's because there. Now, in this case, when the gravity is dominant, de Gennes worked out a relation between the thickness, the puddle thickness, and the other physical parameters, which is given here. That's the puddle thickness and the surface tension, density, etc., gravity. So with this, notice that this only valid when the gravity is dominant. So with this, we can compare quantitatively between the simulation and the theory. So here, this basically shows the puddle thickness as a function of different gravitational accelerations. And this curve shows the relation given by de Gennes theory. We can see that when the gravity becomes large, indeed, their agreement is very good. Now, this slide shows the effect of the oil-water surface tension, this with a normal gravity. In this case, the oil forms a puddle in all cases, but we can see that the puddle, the shape and the size, they are different. So basically, when the surface tension is larger, the oil puddle becomes fatter. This is actually consistent with the relations. Now, so again, we can measure the puddle thickness corresponding to the surface tensions, and here we plot the thickness squared. The thickness squared based on theory is proportional to the oil-water surface tension. The line shows the de Gennes, this relation. Circles show the simulation. Indeed, their agreement is pretty good. All right? So this is an important slide. So here I want to demonstrate the effect of the reduction consistency. Now, the liquid lens here, this is a three-phase problem consisting of the air, water, oil. But equally, we can consider this as a four-phase problem, for example, consisting of air, water, oil, and another liquid like F1. But here, F1 fluid is absent. So basically, we can simulate this as a three-phase problem or as a four-phase problem, but with one fluid absent. Because our formulation is reduction consistent, we expect that the four-phase computation will give us the same result as the three-phase simulations. So this actually is shown here. So these three figures show a comparison of the profiles of the volume fraction of the oil along three vertical lines, basically in these locations. You may not be able to see them clearly, but there's a solid line and a dashed line. One is the four-phase with one absent. The other is a three-phase computation. These profiles, they overlap with each other exactly. So basically, they demonstrate we get the same result. Now, how did we do the fluid is absent? So basically, we assume that t equals 0, the volume fraction of the F1 is identically 0. So basically, at t equals 0, the fluid F1 is absent. Based on physics, this means that if fluid 1 is absent, then over time it should remain absent over time because there's no physics to generate new fluids in the system. There's no chemical reaction. There's no mechanism to generate new fluids. Now, this figure shows the time histories of the volume fraction of the absent fluid of the F1 over time. That shows the maximum norm and the L2 norm, computed using two methods. This figure is computed using a reduction consistent formulation. This one is computed using a reduction inconsistent formulation. So you can see that with the reduction consistent formulation, the volume fraction of the absent fluid basically remains machine zero over time. But with the reduction inconsistent formulation, you can see that the volume fraction of the absent fluid, initially absent, increases rapidly to a significant level. This is about 0.1, the maximum norm. So basically, this means that the initially absent fluid is artificially generated over time when you compute it using a reduction inconsistent formulation. All right, the second problem I want to discuss is a equilibrium configuration of some liquid drops on a wall. This will use the constant angle boundary conditions, so I don't have time to discuss that, but let me only show you some of these. So here, the domain initially filled with air, we have two drops, one water drop and one oil drop, initially far apart on the wall and held at rest on the wall. T equals 0, they are released and starts to evolve and then eventually reach the equilibrium configuration. We want to study the equilibrium shape of these liquid drops. Now, because these liquid drops are far apart, so their interaction is weak, so therefore the shape will be the same as in the cases where each drop is alone in the air. So this allows us to, because this is a three-phase problem, this allows us to compute the three-phase simulation results with the de Gennes theory about the equilibrium two-phase drops. So we assume that the gravity is 0, so the drop will form a circular cap, and then this figure shows the equilibrium configuration corresponding to a water constant angle 135 degrees, the oil constant angle 75 degrees. And you may not see that clearly, but there's a circle there. That's the exact theoretical results, basically with the same volume, with the same constant angle, etc. And with the equilibrium configuration, we can measure the spreading length and the drop height. And then in this figure, we compare these quantities as a function of the constant angle between the de Gennes theory and our computations. So we can see that the agreement is pretty good within a wide range of constant angles. Of course, when the constant angle is very small, the discrepancy becomes more pronounced. This is also an important slide because this demonstrates the effect of the reduction consistency. So these figures show a equilibrium configuration corresponding to a water constant angle 120 degrees. This is 90 degrees for the oil, computed using four methods. These four methods, from top to the bottom, the reduction consistency of these methods becomes worse. So this is a reduction consistent method. This is a reduction inconsistent method. Some of them that sort of in between. We vary the model. We vary the constant angle boundary condition, etc. What we observe is that you may not see this clearly, but there's a zoom in the figure. With the reduction inconsistent methods or less reduction consistent method, what you observe is that the air-water interface forks at the base of the water drop. It turns out that a certain amount of oil is artificially generated at the base of the water drop. So this causes the water constant angle to deviate from this expected value 120 degrees severely. And so basically this demonstrates that the reduction consistency is very critical. It's critical to capturing the constant angles correctly. Otherwise, you are going to generate all these artificial, unphysical results if your model and your constant angle boundary conditions are not reduction consistent. All right. So lastly, let's look at a multi-phase jet problem. Sort of the previous test, those are only static. The equilibrium configuration, this is a dynamic problem. So here again, this is a 2D. The bottom of the domain is a solid wall. All other three sides are open. So here, initially, the domain is filled with water, and then two kinds of liquids are introduced, a lighter liquids than water. are introduced into the domain through two inlets at the bottom wall. So these lighter fluids rise through the water and then eventually move out of the domain through the open boundary. And for these to work, combination to work, the open boundary condition will be very important. And otherwise, it's really for these, when the density ratio, viscosity ratio becomes large, and then it really cannot work. And also, the surface tension will go through the boundary, the surfaces. So these movies show the motion of the two liquids, basically the lighter liquids, in the domain and in the velocity field. And of course, I didn't talk about how you deal with the open boundary conditions for for these kind of problems. But there basically you need to satisfy also the thermodynamic consistency and the reduction consistency. You need to come up with these boundary conditions. So the take-home message talk is this: reduction consistency is really critical to capturing the physics of the n-phase systems correctly and accurately. And what we did is basically we have explored the implications of these two consistency properties, thermodynamic consistency, reduction consistency, on the formulation, on the modeling, on the simulation of the n-phase problems. And we have developed a quite general method for systematically constructing fully reduction consistent n-phase formulations. And with this, we have given a specific reduction consistent and a thermodynamic consistent n-phase formulation. And thank you very much for staying here with me and for coming here. And I would like to stop here and entertain some questions.
Okay, we'll have time for questions.
Just a stupid one. The movie you show seems to be periodic. Was it periodic or just restart?
It's not periodic. It's actually we somewhere.
You stop it and
Right. The stopping and then is sort of if you look at that, the last frame and the first frame, they're not the same, but they're similar. It's not periodic. Yes.
When you split this implicit explicit components with density and viscosity, you presume you can end up with a situation where you have quite a large explicit term. And do you ever see strong stability restrictions of those terms being on the right-hand side?
So what we, based on the experience, is actually that I imagine there will be that effect if you're so basically your nu zero should mimic that field more or less in a certain sense. But what we observed is that if you in these computations, what is more restrictive is actually if your density ratio is large, and then your delta T really cannot go up. I don't have an implementation of the energy stable schemes, but what I suspect is that with those schemes is the same thing. The density ratio really will if you want to get the reasonable results, you're really, even if the scheme is energy stable, you cannot go very large.
So in your cases, you've got a water-air interface, so I guess you've got 1,000 times already.
Right. Yes.
So if you had done that same simulation just with the single phase, would you have had similar time steps? Or?
It is smaller. With this, it is smaller. There are actually several issues, not only the viscosity. There are the density ratio. There is if you look at the pressure, there's also similar term. And of course, there's the CFL, condition.
So, as I understand it, these plots that you're showing a certain volume fraction, they're Fresh-Hofford, right?
It is the CI equals 1/2.
Yeah, so what determines how smooth the C variable is, the volume fraction variable is?
If you look at the phase field equation, the right-hand side, there's a term, is a higher order term. That's sort of similar to the smoothing effect. And so so with that term, you will not get the corners, like the level set, right. But that term comes from physics. It's not arbitrarily put there. So if you derive that in a thermodynamic consistent way, because of the flux, that basically comes from I didn't mention that, but the bulk velocity is the volume average velocity. If you look at that, the individual velocity, there's a difference. And that term eventually, if you use the second law of thermodynamics, that will give you that term, that fourth order term. It comes from the second law of thermodynamics.
I have another question. When you go to 3D, there are special restrictions on joining angles. Is the model able to predict something about it?
Joining angle, you mean the interface?
Yeah, you cannot arrive with any angle in 3D.
Everything is here in the physics. So that actually will be determined by, because there's a pairwise surface tensions. All of those there. I didn't talk about those. In the model, there's a lambda ij in the free energy density function. So there's a relation between the lambda ij and the pairwise surface tensions.
Yeah.
So with this model, basically, if you give me n densities, n dynamic viscosities, and these sigma ij, the pairwise surface tensions, the model will give you the dynamics. So it's actually, there is a relation there. That's coming from the first, the consistency condition. That is, the free energy density function should be reduction consistent. That's the first condition. That will give you exactly the lambda ij determined based on the pairwise surface tensions. I didn't mention that, but there is a relation there. So that will, with that, basically everything, the interface, the motion of the interface, and how they become balanced of those forces, the model will automatically give you that. You don't need to specifically the.
When you were actually solving all these Laplacians, we are somehow also changing the type of physical properties of your scheme. And in particular, you need extra boundary conditions, I guess, which are suitable for the Laplacian, and they might not be in your original scheme, your original couple problem, because the original couple problem has a different nature, right? You have compressible fluids, you have visible and invisible fluid. So the original variables might require boundary conditions that are not those that you need to solve your separate Laplace equations from different variables. Am I wrong?
So here we assume all these individual fluids, they are incompressible. And then if you use I mentioned just a moment ago, the velocity there is a volume average velocity. And you can regularly show that there's a definition. Basically, from the individual fluid, the velocity, from the flux, I divide it by the density or the mass, you get the individual velocity. From there, I define the bulk velocity. And basically, that's the volume average, the Ci times the Ui individual velocity, add them up. That'll give me the bulk velocity. From there, the step by step, you can show that defined velocity is exactly divergence free. If you use other velocity, it's not divergence free. So based on that, everything coming from there, those several things, I can exactly derive these conditions. And then their individual fluid, they are incompressible. And I have the corresponding boundary conditions. I didn't show them here. Basically, I want to conserve the mass of the individual fluid components. And also, the other one will give me the constant angle boundary condition. And I didn't show those there. But those boundary conditions are coming from physics.
Other questions? So I guess it's possible to develop energy stable schemes, right?
I think so. The main difficulty here is that the Mij is a function right now. But the matrix, it is the semi-SPD. So everything there's a energy relation, the energy law. So in principle, we should be able to develop that. But again, when you have that scheme, there will be all the issues like the Mij. All of those will go inside. Your how to when you compute that. I'm not sure overall. In terms of the cost and the delta T or the other gains, whether the overall whether it is favorable or not. But yes, I certainly because we have the energy law on the continuum level, it should be possible to develop a corresponding discrete counterpart.
You can have an energy stable scheme, and then you can use this as a precondition.
Yeah, that would be that's
so
probably.
You will be able to choose different time step by different.
I think so.
Okay, so if not, let's thank Steve again for the. Okay, that's the end of the ICOSAHOM. But before we leave, let's thank the local organizers, especially Spencer, for a wonderful organization. And see you all hopefully, see you all in Vienna in 2 years. Okay? Have a good afternoon.